Everyone. Welcome back to the second day of the workshop. Just one announcement. So at 4 p.m. at the end of the talks today, we're thinking of hosting an open problem session. Just like this, like an informal session where people can come up to the whiteboard and list their favorite open problems that we'd like to have solved. And this will happen at 4 p.m. today. So it'll just be a 1 hour open problem session in this room. So with that said, I'm happy to present Sebastian Forster from the University of Salzburg. And his talk will be on dynamic algorithm case on graphs. Sebastian Forster is an assistant professor at the University of Salzburg. He completed his PhD at the University of Vienna in 2015, where he was supervised by Monika Hensinger, and was then a postdoc at Max Planck Institute of Informatics, and then at University of Vienna. His main research interest is the design of efficient graph algorithms, in particular for dynamic and distributed models.
So I'm talking about dynamic algorithms for K-center, for clustering. I somewhat chose this topic because it nicely connects to work on dynamic shortest path. This is a topic that I have worked a lot on, and I know that many in the audience have worked a lot on that. So I think this nicely fits this theme. This is joint work with Emilio Cruciani, who's a postdoc, Gramoz Goranci, who's around, Yasamin Nazari, who wanted to come but couldn't because of visa issues, and Antonis Skarlatos, who's a PhD student. So yeah, the overall motivation, I mentioned this in this short lightning talk yesterday, was, okay, maybe, you know, we like to do these dynamic algorithms, and then there are people who work on, like, say, network science, and for them, like, dynamic is something very natural. They often have this idea of, like, yeah, you know, we study evolving networks. And the idea is just, how can we bring these two things a bit closer together? And yeah, clustering is like one of the natural connecting points, I would say. Like, you know, how could we then do something that might be somewhat of interest to people in more like that community? And the main point here is, like, I'm talking about clustering on graphs. So there have been dynamic clustering algorithms. Ours is not the first. That's a well-studied problem. But these algorithms that have been studied are somewhat not tailored to graphs. And now you might say, maybe that's a good thing, right? Maybe something more general is actually good. But I'll mention or I'll explain in a minute, like, why we really need, like, tailored algorithms for this setting. At least for the setting that we have in mind, that would make sense. Okay, just to quickly remind you, what's this K-center problem, the K clustering problem, a K-center clustering problem. So we're given a metric space with points, and we want to select K points as centers. That would be the cluster centers. Say K is 3, and I would select those 3, for example. And now I want to say, okay, every node chooses, every point chooses the center that is closest to it, and joins the cluster of that center. And now there's a natural thing that these clusters have a radius, like what's the furthest away point for every cluster center in that cluster, and that's the radius of the cluster. And in total, we want to minimize the maximum radius in our clustering. Okay, so this is this distance of any node to its closest center. That is what we want to minimize. Okay, as often these problems are somewhat hard, and be hard to approximate this within a factor of 2 minus epsilon. So the focus is usually on constant factor approximation. Okay, so I mentioned before, this has been studied on metric spaces, on point sets. Yeah, so we have a set of points, and we have a metric, this function d, like a distance function on the points. It just has these satisfies typical axioms for a metric. And in a graph, the pairwise shortest path distances induce a metric with the nose as the point set. And now my question is, can we get dynamic constant factor approximation algorithms for this K-center problem if the metric is induced by a dynamically changing undirected graph? So that's the objective. Okay, now let me explain shortly, like, unweighted or weighted, so both things. Okay, so what's the dynamic model? I said there are subtle differences, like in dynamic point sets, we have insertions and deletions of points. Like, say we have these points, and now we just add an additional point, and that's it. In dynamic graphs, say we have this graph, and we insert this additional edge. Yeah, then there are many changes in this metric, right? So here it's more like, okay, we extend the metric by this point, and the other points are somewhat unaffected. And here it's like, okay, we insert this, and then it could happen that like omega n square pairs change the distance, so the metric is changed a lot. So my intuitive view is a bit like here, yeah, the metric is extended or reduced by points, and here it's more like I'm actually, by inserting, shrinking the metric, modifying the whole metric in a certain way, or if I delete an edge, I'm expanding. Another subtle thing is that here I would assume that the distance is not given a priori, so it's the task of the algorithm to maintain these distances and the metric, or like the relevant parts of it. Whereas here it's usually assumed that one has query access to distances to this D function, the metric. And that's somewhat natural if you consider, for example, point sets in a Euclidean space or something like that. You just say, oh, you have the coordinates, and then the distance you can just simply compute by looking at the coordinates. It's a natural thing to have this query access.
Are you also going to shrink the set of vertices of the graph that you potentially care about, or you always keep the same vertex?
So the formal assumption would be to keep them always the same. I mean, you could delete all edges of a graph, and then, okay, you always have to, then it's a bit tricky, right? You would have to restart them, because this one always needs to be a center if it's not connected to everything. But yeah, you have to somehow deal with it in that way. So, yeah, maybe it would be nice to formally treat this explicitly. Okay, so the conclusion here is we cannot use prior work that has been designed for dynamic point sets in a black box manner for the dynamic graph model. But still, this has been like influential work. So let me briefly tell you what is the related work. Okay, there are static algorithms, and there are these classic two approximation algorithms. And on graphs with n nodes and m edges, you can implement those in roughly k times n time. Pay a log maybe for Dijkstra, depends on the exact setting. And there has been very nice work. On graphs, you can get rid of this factor k. We showed how to do this with a randomized algorithm in nearly linear time. And then there's a nice recent Sousa paper that shows like how by a nice view of randomization, you can also do this in linear time with an arguably simpler algorithm. Okay. So, and what's known for like dynamic point sets, case-hinton dynamic point sets. So the first was a result that had like a k-square update time that also very recently, in an effort, including many people, for example, Monica, reduced this to a tilde OK update time. And those works also give 2 plus epsilon approximation. And then there has been even more work on point sets, like looking at special metrics, say bounded doubling dimension, or looking at a somewhat extended question of how do you dynamically maintain a consistent k-center clustering for whatever the exact definition of consistent is. Okay, so that's roughly where we are. And now I would like to argue that a somewhat natural goal for us would be that, maybe we want something that is roughly comparable to this like very classic deterministic result that has an update time of k times m. So roughly speaking, this is k times the time you need for a static single source shortest path computation. And so somehow the natural thing that I would argue to get is now we want a fully dynamic or fully dynamic, partially dynamic algorithm such that the overhead compared to an approximate single source shortest path computation is like an okay or tilde okay. So I would argue this is like, the natural first goal if you want to study this problem. And yeah, somehow I set it up now in such a way that I can give you the good news, and that's exactly what we get. So the first thing is we have a fully dynamic algorithm that gives a 2 plus epsilon approximation to that problem. And it has either this update time or this update time. So it's k times this n to the 1.5 to 9 or k times n to the 1.8 to 3, depending on whether you're in an unweighted or weighted graph. So some of you might know what's going on here. Those are the update times for fully dynamic 1 plus epsilon approximate single source shortest path. And for fundamental reasons, those algorithms, yeah, Jan is walking in right at the right time. For fundamental reasons, these algorithms internally use fast matrix multiplication. So this has some explanation given by conditional lower bounds.
So are there any reductions either way showing that like you can't beat the 1 plus epsilon approximate SSSP times?
So only like, morally or intuitively, I would argue that somehow what you want, right? Somehow I think you do want an approximate distance to your cluster center. And but it seems hard to go below that, right? It's a bit like, yeah. So say, for example, you want to give a 2 approximation of the diameter, right? Then essentially the best way of doing this is run a single source shortest path computation from an arbitrary vertex. And I would say this k equals 1 case already is very similar, right? You have one cluster, but you somehow, I guess you want to know the distance to the cluster center. So unless you change the problem to something where you don't want to have this distance to the cluster center explicitly, it sounds very natural to me that you cannot do better than shortest path.
What is your recourse bound?
The question is, what is a recourse bound?
What is the recourse bound? Here it's not really bounded, like k per update, right? In the decremental, I would have to check, and in the incremental, we have to really explicitly work on the recourse.
Okay, so in the fully dynamic setting, it can be k per update, where k is just basically just the trivial thing, that the number of centers.
Exactly. K would be the trivial thing, and here's it's the trivial. Okay, so this thing is a reduction. So any single source shortest path, approximate single source shortest path algorithm you have, if it works against an adaptive adversary, you can use that.
A quick follow-up. Is there a lower bound? I have no other question, just this. Is there a lower bound for recourse which says that you can't do better than k?
I don't think so. I'm not aware of it. I think people have studied recourse very explicitly also. Maybe you can say something about it.
Sorry, I was actually asking a different question.
But yeah, I'm not aware of it, and people have studied recourse very explicitly. Recourse means like how much do you change these k centers from one update to the other? And here it's like we don't even try. We must.
Yeah, so my other question was, what kind of assumptions do you need to make on this 1 plus epsilon approximate SSSP? Does it need to maintain the distances explicitly, or?
So I'll talk about it in a minute, but let's answer it already now. So it has to be against an adaptive adversary, and it needs to maintain the distances. You need to be able to like query the distance in whatever small time.
Query model, not like an explicit matrix.
Yeah, I mean, if you have like, something like you do single source shortest path and you have like super linear time, then in the same time you can just like query like the distance to the source for everything. But like while we're at it, like something that's interesting, I think, is you do need that it works against an adaptive adversary, but in some sense you only need these approximate distances, right? unless you really want to have a path from the node to the center. But if you do not care about this, you just want the clustering, then you do not need this. So it's a nice example of like, oh, you need like something that works against an adaptive adversary, but the value version is good enough.
So the dynamics SSP algorithms, these are randomized, or are they deterministic?
Yeah, okay. So this one's deterministic. This one's randomized against an adaptive adversary.
And if your external K-center algorithm was, if you just wanted the result for oblivious adversary, would you be okay with oblivious adversary SSP algorithms?
I don't know how to do it because I'm doing a reduction that's inherently adaptive.
So if in addition to these updates, you're also giving query access to the direct weights, I guess then you should be able to just black box use the existing works on
I'm not so sure, right? Because as I argued before, right, if you just insert one edge, you could change the distance between many pairs of nodes. And that's just a different model. Like even if we did that, like have a distance oracle or whatever, and then say even if it was able to like quickly give us query access, it's a bit unclear. So I don't see how you bring these two things together in a All right, so that's a fully dynamic thing that will work via reduction. Then the results on partially dynamic are now particularly interesting, right? Because, yeah, somehow it's a natural goal to have something like this, but single source shortest path in the fully dynamic setting just stands here. That's just something we cannot really avoid here. So similar to single source shortest path, now it's the question like, what could you do in the partially dynamic setting and in the decremental setting with edge deletions? We get an overhead of k. So there the update time is k times n to the little o1. So again, that's in line with what we have for approximate single source shortest path, n to the little o1 update time. And then in the incremental setting, like we have edge insertions, we also get this. But there, it's actually a bit challenging, and I will tell you later why. And we get a 4 plus epsilon approximation, not a 2 plus epsilon approximation. And we really need to exploit oblivious randomization here. Yes, this decremental one that you can make deterministic. Using powerful approximate single source shortest paths that are deterministic. Okay, so now this reduction that's, I think, nice and easy. Here, again, a reminder, how does this one type of two approximation work? It's this algorithm that starts with an arbitrary first node as the center, say this one, and then just takes the node that has the maximum distance to the center and says, okay, that's my second center. And then you go on. You find the node that maximizes the distance to these two nodes simultaneously. Say it's this one, and this will be the third center, right? This is this heuristic. This gives a two approximation, and it's somehow not sensitive to the distances being exact. If you only have like 1 plus epsilon approximations to this distance, this will give you a 2 plus epsilon approximation. That's what's going to happen. Okay, now the reductions as follows. We want to simulate this algorithm using a single source shortest path algorithm. So to this graph, I add some artificial supersource that's outside of the graph, and I start now maintaining single source distances from this node. And initially, it's not connected to anything, but the algorithm internally has to do something already, somehow has to prepare for stuff. And now, after every update to the graph, what I'll do, well, first I forward this deletion or insertion, the update to that graph. This approximate single source shortest path data structure does something internally. And then I start simulating now this Gonzalez algorithm. So after every update, there's a new simulation. I just say, okay, take an arbitrary first center, say this one, C1, and connect it to this supersource S. And now I want to find the node that's furthest away from C1. And that I can do by finding the nodes that's furthest away from this node S. That's C2 here. Okay. And then this is also connected to the super source again. Now I find the node that's furthest away from S, and that's just the same as saying I want to find the node that's furthest away from these two. Okay, this is a +2 systematic, a +1 systematic overestimate. So I can use the distance to the supersource as the proxy of the distance to this node, this set. Okay, and when I'm done, these are my centers, and then it's a fully dynamic algorithm. I just remove these edges again. I do deletions, so I'm done. And the important thing here is this is highly adaptive. The algorithm needs to work against that. So otherwise, this already doesn't work. Okay, so the update time, it's a reduction. It's O of k times whatever the update time for my approximate single source distances is. Okay, questions so far? Okay, so somehow this is good news. This is nice, but maybe on the other hand, it's not so deep. So it's somehow justified, I guess, both in terms of techniques and in terms of getting the fastest possible running time for different settings to now look at partially dynamic algorithms. Okay, and now these are, if you know the clustering literature a bit, these are now based on this other type of two approximate heuristic that's based on R-independent sets. A bit like in Mikkel's paper. So what's an R-independent set? It's a set of nodes such that any pair in the set has distance more than R. Yeah. Independent set would be all nodes, all pairwise distances must be more than 1. They are not neighboring, and you can generalize this to any R. You can also, again, look at this notion of maximality, such an R-independent set is maximal if it cannot be extended without violating this property. Okay. So how could you compute a maximal R-independent set? Yeah, for example, by this standard greedy algorithm, you start with some first node as being part of your R-independent set, then check what are the nodes that are within this radius R from that node. You take them away from the graph, start with some arbitrary second node now as a node in the R-independent set. Do again this thing, take all of them that are in distance R away, and so on. Okay, and that picture suggests already somehow, yeah, you want to, in the end, use these R-independent sets as your clusters. You just need to find what's a good radius for doing that, and you need to argue why is that then a good approximation to K-center. We'll often talk about something that's called K-bounded maximal R-independent set. What I mean by that, if I say that, is, well, if the set has size less than K, then it is a maximal R-independent set. Or if it has size K, yeah, then it could be one or it could be not, but somehow conceptually it just means I'm not extending this computation any further. I just want to know, do I have a maximal R-independent set of size at most K or not in many cases now? And yeah, when that's relevant, I'm writing K-bounded maximal R-independent set. Okay, and this heuristic, this two approximation, is essentially just saying, yeah, find the smallest value of R that's possible such that the maximal R-independent set has size at most K. Yeah, if it has size at most K, you can use it as a solution to K-center. And if you find the smallest such value, then you get a two approximation. So the algorithm is roughly like that. Yeah, you guess your R either by doing an outer binary search or doing this for powers of 1 plus epsilon. And then you compute the maximal R-independent set, say, by this greedy algorithm. And if you have more than K nodes in this R-independent set, then somehow you cannot cover the whole graph with any arbitrary R-independent set. So you want to increase your R. If you have less than K nodes, you want to try to decrease the R until you, yeah, by this search, find the right one.
Is it the monotone function? Because it's computing maximal, right?
Yeah, it's a bit like, subtly depending on the choice of like the permutation of how you.
So you can make it monotone, right?
Yeah, you don't really need to like for example these powers of 1 plus epsilon, just do it for all powers, and it's good like for at least for us we do not so we do not need to deal with this right now. Okay, and again right here it suffices if I compute like this k-bounded maximal R-independent set and check if it's indeed maximal. I don't have to like do this whole R-independent set computation. That's just sometimes relevant in terms of running. Okay, and then the nice lemma is if I chose my R big enough, so opt is like what's the minimum radius I can get from an optimal k-center solution, then every maximal R-independent set has size at most k, so I have the guarantee that I will be successful. Okay, that's the black box thing we use from prior work. Okay, and again, if we have 1 plus epsilon approximate distances, we get a 2 plus epsilon approximation. Not a nice 2. Okay, now I'd first like to tell you how we design the decremental algorithm. So if the graph's undergoing deletions, that's somewhat, I would say, in line with how other designs work for like similar problems. So distances are non-decreasing over time. You delete something, then nodes cannot get closer together. They can only increase in distance. So if you have an R-independent set, it will always continue to be an R-independent set. The only thing is maybe before it covered the whole graph, and then some distances increase, and then it doesn't cover the whole graph anymore. But the parts you have from your R-independent set, they don't go bad. That's the heavy thing you can exploit here. So the scheme is like you have a guess of R that somehow increases over time. And for your current guess of R, you increase the number of centers you have also over time, right? First you try to do it maybe with k equals 1 center, then maybe 2, 3, until at some point maybe k centers do not suffice anymore, and then you need to increase your guess of R. Okay. And how we do it, similar to this reduction before, we maintain decremental approximate single source shortest path from some kind of super source that's connected to every center that you currently chose. And after each deletion, you update this single source shortest path data structure. And if some node is not covered anymore, if the distance is more than 1 plus epsilon R to any center, then you check, right? If you exceeded your budget, if you already have k centers that you chose, then your guess of R is not good enough anymore. You need to increase it and do the next phase of your algorithm. Otherwise, you can now, similar to that greedy algorithm I showed you before, simply add this node V to your current centers and restart the decremental single source shortest path algorithm, right? Connected to the super source, you have more connected to the super source and connected. Okay, so just want to show you a picture from what I said before. So say these are the current clusters. These are my single source shortest path type of things. If I delete something, then what could happen? Yeah, this node could somehow have to leave this cluster from that R-independent set, and it has to like start its own thing. That's what we do in such a case. Okay, so what's the total update time? The main question is how often do we need to start single source shortest path? So this is like total update time here. So I can only think of like, in these single source shortest path data structures, I can only tell you, okay, what's the time for running them like until everything's deleted. It doesn't matter how many deletions I do. So that's why this doesn't depend on the number of deletions. And so the update time is roughly like this. Like for each guess of R that I make, for each scale, this set C increases at most k times, because I'm looking at k center. So this decremental single source shortest path algorithm is restarted k times a logarithmic value times here. lambda is this aspect ratio of the graph. In an unweighted graph, I would do log n here because the maximum distance is n, like the distance increases most from 1 to n. If you have a weighted graph, then somehow you need to think of what's the maximum distance you can increase. So it's a logarithmic number of times k that you need to restart your sinusoid strokes. So that's the scheme for the decremental algorithm. Okay, and now somehow hinted at it. That's somehow nice, but the real problems start with the incremental algorithm. Okay, I omitted this. Yeah, you can do this randomized or deterministically. So now we somehow like to use the same scheme, right? And say, okay, yeah, I insert stuff, so distances never increase, things only become closer. Can I do the same? Can I exploit this? And yeah, to some extent, right, this whole idea of you have the scale and it reduces, that still works.
I was confused about one thing, like, I was just confused in the last about the update time.
Sure.
Do you need to like query the data structure on every single vertex?
Yeah, that's one of the details that I've omitted, right? So this data structure, it tells you explicitly when the distance estimate of a node increases.
Okay.
Yeah. And that works because it's a 1 plus epsilon approximation. So you don't have a recurse problem because for every node, it can only increase like in 1 plus epsilon steps a logarithmic number of times, logarithmic in 1 plus epsilon. Yeah, that's one of these details that are somewhat a bit standard that I thought. Okay, so incremental, we would somehow like to use a similar scheme, but the problem is an R-independent set will not necessarily continue being an R-independent set. And the most extreme thing is like, say you have this R-independent set and you just insert an edge between the two centers, right? So then, of course, right, these two nodes are not independent anymore. So there could be conflicts after insertions. And then that means we somehow need to update or recompute our set C, our R-independent set, because we want the number of centers to be at most k, right? If you don't do this, then somehow we might have things that are overlapping and the whole correctness proof doesn't go through anymore. So we need to do something. But why is it non-trivial now to do something? For every node in this R-independent set, we maintain approximate single source shortest paths. Now, changing C is therefore expensive because every time we put something in C, we pay like at least a linear, or n to the 1 plus littler 1 update time. We cannot bound this any better, right? Just to initialize it, we need linear time. So the total update time will be the number of nodes ever contained in the set C times m to the 1 plus littler 1. Okay, so I want to keep this small. This is like the recourse, and it's the total recourse. Okay? How much changes do I make to C over the whole update sequence? That's what I want to keep small. So I want to maintain an R-independent set with low total recourse. Okay, and to analyze this, there's in this Bateni et al. Paper, there's a nice view on it. I think it's original to that paper, so at least we've learned a lot from that. So now conceptually think of doing what's called this R neighborhood graph. So that's just like for every node, and just connect every node to every other node that's in distance R of it. Okay, like this. You can do that for the whole graph. And then an independent set in this neighborhood graph GR, that's just an R-independent set in the original graph. Okay, so now I'm asking just a very basic question about the total recourse of maximal independent set, which is a well-studied problem in dynamic algorithms. Okay, one thing here, like I'm not constructing this neighborhood graph in the algorithm, it's more of an analysis tool. And all that I really do is I compute k-bounded maximal independent sets on this neighborhood graph, and for doing that, I partially construct it, but only to the extent that is necessary. And for those that are really into the details here, it's actually not so easy. As you notice here, I'm using exact distances. You would have to do this for approximate distances. If you want to be formally clean, it's a bit tricky. But just to say it completely, it's also not necessary. It's just an analysis thing. You could directly analyze it without this neighborhood graph. Okay, so we want to maintain this k-bounded maximal independent set in the neighborhood graph, and we want a total recourse that's polynomial in k, ideally something like tilde OK. And since the input graph is incremental, this neighborhood graph is also incremental, and yeah. But what bound can I give, right? Even if my input graph is sparse, this could be dense, and I could have up to, say, n square insertions here. And to the best of our understanding, we do not see how the MIS algorithms that are known provide a good bound on the total recourse. They are known to have like, I think even constant recourse per update, but now you cannot just say, okay, overall you have like a M update, and somehow stating it the way I did here is a bit oversimplifying, right? Because now I'm not exploiting that I want a k-bounded MIS and not like a full MIS. And yeah, we didn't find a way of doing it with an MIS.
I'm not sure about the recourse. I'm not sure about the recourse of the MIS algorithms.
Like you don't?
Like,
but I mean, they have polylogarithmic update time, so that trivially bounds the recourse.
no, because so the paper of Chechik and Zhang, and also of Sohail and others, they are using multiple copies.
I see. But you don't need a worst case bound here, right?
If you want, yeah, if you want worst case.
No, no, definitely not a worst case bound. So this is an amortized bound here. Because also the single source shortest path approximates.
Okay, amortized, it's actually 2.
Yeah, that's, I shouldn't have a tilde here, right? It's a constant. Yeah. But yeah, good that we clarified this. Okay, so we came up with something else that's more like we want to have a dominating set on this neighborhood graph, and that dominating set has small total recourse tilde OK. And then we maintain a k-bounded maximal independent set on the dominating set, or on the subgraph, like say this is the dominating set. Then we have the subgraph induced by the dominating set on the neighborhood graph, and then we maintain an MIS on that. Okay, and in that way, we can guarantee that every node is at a distance at most 2 to a center in this MIS in the neighborhood graph. So in the real graph, in distance at most 2r to a center. So that's why it gives in total a 4 plus epsilon approximation. Okay. And now I'll just quickly sketch how to do this. So there's a sampling algorithm. Of course, right, you cannot just have a dominating set that's small always. There's one catch here. So we do random sampling. We sample k log n nodes uniformly at random, then remove the sampled nodes and the neighbors from the graph. And if now I have more than n half nodes left, then we can say there isn't an MIS of size at most k. That scale is not good for us. So that's the catch here. That's where we use something problem specific for this clustering problem. Then we would, in our algorithm, move to the next scale. Otherwise, if we have only n half nodes left, we just iterate. Okay. And I'm skipping this proof, but if I reduce, of course, like the size here always by n half, then I only have a logarithmic number of such stages. And it does work because of I can stop in that case if there's no MIS of size. So this is a static algorithm. The incremental algorithm is very similar. So almost the same analysis would work then. And here the important thing is this algorithm that works with sampling and removes the neighbors of the sampled node from the graphs, that only needs access to the edges incident on that set S in GR. And because for those nodes in the set S, I will have do a single source shortest path computation. I know somehow what the neighbors in the neighborhood graph will be. And that's why I partially construct the neighborhood graph, and it just works within the running time. So I think we can skip that proof, like why if I have more than n½ nodes, I don't find a small MIS. That's standard hitting set stuff. We can skip over this. And so it remains open, like, could I really maintain a k-bounded MIS with polynomial total recourse? That would be nice. I'm skipping that also a bit. That would be nice, because then I could maybe get this 2 + epsilon approximation. I somehow have this intuition that even if it worked, maybe this would be more like a k-square recourse and introduce another factor of k in the running time. And the reason roughly is, like, if you would do random insertions, then that's what, like, this k-square would be what you would get for the total recourse. And the intuition is maybe you cannot do better than random insertions if you have an algorithm against an oblivious set. So if you'd like to talk about this, this is like the interesting problem for that particular thing there. Okay, let me conclude. So I think this is a nice application of dynamic approximate single source shortest path. Brings a lot of things together that have been developed over the past years in that area. And one thing I also mentioned, maybe path reporting actually seems a bit less relevant in that context, unless you really want to find the path to the center. But if you just want to cluster, the distances seem fine enough. Incremental was somehow the difficult question for this problem, because it somehow had this MIS question that was somehow in there, right? And I think that's somehow really what was interesting for me to see, at least, that you have this single source shortest path component and the MIS component, and it somehow goes together. And one thing I want to say is, maybe as a community, I made this point several times, maybe incremental model is actually sometimes more relevant than we consider. Yeah, you usually have this like feeling, oh, decremental is the hard thing, and all the techniques just transfer to incremental. So it's definitely not the case here, as with MIS as well. And incremental is maybe a bit more natural than, say, decremental, because you have these things like social networks where it's more likely that you make friends and the graph gets more connected than you delete friendship relations. Or like, Wikipedia links. No, co-authorship graphs is an even better example, right? You make new co-authors, but you rarely lose co-authors, right? So this type of social network analysis, I think incremental shouldn't be underestimated. So future work for us will definitely work more on other clustering objectives in graphs instead of concepts. And it would be interesting now, I think, to engineer and dynamic approximate single source shortest path algorithms, because I think somehow the rest of that algorithm that I've presented here, that's somewhat very friendly to implementations. The single source shortest path is not, but if you had a nicely engineered black box, maybe you could then plug it into the algorithm. Okay, thanks for your attention.
Thanks, Sebastian, for the great talk. Any questions?
Thank you. Is there something known about conditional lower bounds? So like I had in this earlier paper with Saga, I had a conditional lower bound for 4 - epsilon approximate k-means, for example. So there are lower bounds even for clustering problems.
Yes. I'm really not very familiar with it, I must say. And I guess I would, like, maybe we can talk, right? Like, the question for me is, like, do these lower bounds definitely transfer to dynamic graphs, or is there some technical detail while they don't directly transfer? That's something I think we should look at.
Okay.
Just a follow-up to that question. Is there any hope of improving the recourse or the update time to below k, like constant, irrespective of k?
So it's a bit connected to whether maybe this, say, k times n lower bound applies or not, right? Which I don't know. otherwise, yeah, I mean, it could be done in the static setting, so maybe there's hope to do it in the dynamic setting as well, but it's somehow, yeah, unclear. Like I would say, even in the static setting, it's a bit unclear what you could do with deterministic. So all the settings have somehow still their justification.
Just since you mentioned my old paper. So the general result there was that for both K-center, K-means, facility location, you could solve any of these problems with a polylogarithmic number of single source shortest path computation, essentially spending the same time to evaluate an instance as you would spend constructing it. Well, other way around, yeah. I'm just wondering, since this approach was so general and it does certain kind of updates to code these single source shortest paths by putting exactly these things, I'm just wondering if something more general could be done because of how K disappears and what I did. I don't know, but just
yeah, I think that's just stuff I need to leave open for the future right now. But yeah, I mean, it's
it'd be nice to have a generic result.
Yes, exactly.
So if you want worst approximation, what is the best known update time?
I don't think anything is really known. It's just like, like, okay, worst single source shortest path, right? Like worst approximation we don't really have. So it's a bit the question, like, how do you want to beat like just the single source shortest path time? Maybe getting rid of the factor K with a really worse approximation. Maybe that's not hopeless, but I can only speculate.
So in some sense, a facility location problem is nicer to work with because you don't have this weird bound K, which really hurts you, right? Really matters a lot if they have K or K plus 1 and everything is small, so continuous. So maybe facility location is nicer to work with. I don't know.
Yeah, that's a good suggestion.
Thanks. This is about the worst approximation. So about 5 years ago, we had this paper with Monica and Nicole and others, and we considered the one center problem, so diameter and radius, so radius in graphs. And we looked at the dynamic version. We got basically whatever the static algorithms were, 3/2 approximation with m root n time, they became we got a reduction, basically in a similar way to the dynamic single source shortest path problem, approximate. And again, the incremental case was harder. It was only oblivious. The decremental could make it adaptive. The same story happened there. And I'm curious what happens for K-center if you also, is there a similar notion of a 3/2 approximation as in one center or no? In the static setting? No, nothing?
I don't, yeah, I mean, I don't know if what's the K for which it becomes NP, how?
I think it should be a lower bound.
Even for constant K,
So,
like 3?
Definitely 3. Sorry, 3.
Definitely 3, yeah.
Yeah. Okay.
But thanks for the comment, Virginia. So you call it one center and it's easy to understand.
A quick question. So suppose you have a distance oracle and that comes for free. It takes constant time. Does all these results just imply that you get order K update time in that setting?
I don't think it's clear, right? Because it's not like you insert a point and because even if you inserted a point, that point could be used by others to get a smaller distance. So you would have to
Okay, so what I'm asking is, if your update time is measured just by the number of calls you are making to a distance oracle, then is it still open to get an order K update time under age updates for this problem?
Oh, you mean a clean O of K?
K polylog, I mean ignore polylog.
You need single source distances, right? That's in credits.
Yeah, but the n amortizes out, I think, if I understand Sam's question correctly. So, yeah, if everything's for free.
It's not
Yeah,
clear to me,
something
so
like a
that's why
total
I
k
asked.
times n, then I think could be possible. I'm not sure. I'm not sure. We would have to go through it in detail.
Okay, thanks.
Yeah.
More questions? Thanks again, Sebastian.
Thanks a lot.
All right. So we'll be back at